Again, I'm actually here to talk about establishing real-time collaborative science decisioning systems for the Moon to Mars human robotic exploration. Fundamentally, I'm going to share with you all what I've been focused on for the last 20 years, 20 plus years really, of research in my life, which is really trying to understand how it is that people work when they're doing science, where the friction points are, how we might make that process more efficient, and more geared towards the optimization of science return, particularly when we have the opportunity to make decisions in real time to improve the science return. So, of course, we live in a really exciting moment in that we're considering, this endeavor right now in this room of sending humans back to the moon and then onwards to Mars. And what is particularly exciting is that for so long we've been focused on mission architecture, such as the design reference architecture, which was published in 2009 as an example, where we had somewhere between 4 and 6 people, really form the first crew in that architecture that would go onwards to Mars. But now with some of the transportation opportunities that are coming online, where we can start thinking about 100 tons, 300 tons worth of carrying power, then the size of the crew may change. We may see that the first landed mission involves perhaps 10, 20, maybe even 30 people on the first endeavor. This is all to be seen as architectures come together. My curiosity remains the same as does that of my team, which is to understand how we might work together when humans get to Mars. And when I say we, I mean the team that is on Mars, the team that is on Earth, how they work together, co-located on those 2 planetary systems, as well as how they would work together and collaborate across the timescales, across the latencies between those planetary systems, despite the remoteness. And so the way that I've been going about the research regarding understanding how we might work collaboratively to optimize science return and exploration return once we get humans to these surfaces is to look actually very closely at our home. So I've been conducting field science research across many different work domains as well as environments on this Earth, primarily in the realm of geobiology and astrobiology as being the focal points of the natural sciences research, but then also involving operations research as well as engineering research, always integrated together into these programs. And I've been working to understand and experiment with the terrestrial work systems that these scientists and engineers bring to life whenever we go into the field. And from there, when we can look at these work systems on Earth, we can really then start to imagine, design, and establish real-time collaborative science decisioning systems that help scientists work together, work collaboratively, work in a manner which is in scope, in line, and lockstep with the mission cadence, so the tactical decisional timescales of any mission, whether that's headed back to the moon or headed to Mars or elsewhere. And so these are the types of problems that we've been noodling over every time we go into the field. And I've had the joy of actually working, as I mentioned, in different field environments, from underwater to the, working on the surface of water, working underwater with different operational conditions, as well as working on land in the Arctic, Antarctic, volcanic and desert settings, all with the mindset of trying to understand what principles kind of move between these different environments, the different scientific and exploration goals, and what becomes extensible and constant as we actually find ourselves in these different settings, working with different peoples from different disciplines and trying to bring them fundamentally together in this collaborative work environment. So one of the important elements of the experimental work that we've been doing is to incorporate and address the fact that as we move humanity, beyond these terrestrial environments into space, we start to have to communicate with them over latencies, over communication latencies. So if we're looking at communication between the Earth and the Moon, it can be about a second or more in terms of the transmission, bidirectionally of information. And of course, as we start to get further out towards Mars, that can range anywhere from a little over 3 minutes all the way to a little over 22 minutes one way. And so, of course, you do the math times 2. So there are long communication latencies. Now, what we were interested in many of our projects, our experimental projects in the field, was how these increasing communication latencies would affect our ability to enable and enhance science and discovery during human exploration. And how, the really embedded question in that is, how can we create work environments, work systems that would support collaboration and cross-communication between the different groups as they were working to fundamentally discover as much as they could with every single outing that we have. So recently, I've had the joy of being a part of the Viper, NASA's Viper lunar rover mission, and leading the science operations team for Viper, and taking all of that experimental work that I've been doing over the last couple decades and then applying it towards this mission operations. And so this mission fundamentally was set up to be collaborative. It was really exciting when I joined the team in 2020 for me to learn that all of the instruments on board of the rover were actually meant to work together in a complementary manner. So there are different spectrometers that are meant to sort of enable and enhance the data return from the other spectrometers, in the sense of, we have teams that are specialized, of course, working and examining the data from each of the spectrometers, but each of them will, really helps the other by analysis and understanding as the data is coming in, because they work in a complementary manner. As well, there's imaging from 8 different cameras that are associated with the rover, and then there's a subsurface excavation tool, a drill, that allows us to look directly at the subsurface of the lunar South Pole. And so again, the instrumentation right from the get-go, this mission was set out to do collaborative, exploration. And the mission is actually set out to rove for 100 mission days across about 15 kilometers of the South Polar lunar landscape. And we were to actually traverse 4 different ice stability regions. As many of you know, this mission is currently in sort of a transition state, if you will. We're trying to figure out what happens next, what type of partnerships might come next or not. And so it's been a very interesting journey, I can tell you, over the last 8 to 10 months. But nevertheless, there's so much that we have learned from the establishment of the work systems, the science operations for this mission, that continue to live on and be extensible to further lunar missions, as well as to missions here on Earth that are curious about how we might really enhance science and exploration return using real-time decisional systems. I just want to show you a little bit about the rover and how it is actually set up to explore, to explain a bit about what I do and the application of what I've learned over the last 20 years, working with so many different people who've contributed to that knowledge, in terms of learning how to design science operations for real-time operations on the lunar surface. So when we do get to the lunar South Pole, the rover is actually set up to be commanded directly from NASA Ames in the San Francisco area. And so what happens is that because of the latency, we have a communications round trip really of between 6 to 10 seconds when you take all of the different component parts into consideration. So what that means is that we're actually commanding the rover in what's called near real time. And a lot of people kind of invoke a thought of joysticking the rover across the lunar surface. It's not at all like that. In fact, what we do is our drive team will put down waypoints about 4 to 5 meters apart from each other. And there's opportunity to think about where to place those waypoints each and every step of the way. Even though we go into the mission having planned out all of our traverses based on science objectives, based on our understanding of the lunar South Pole and where the ice stability regions are. However, as anybody in the room knows, once you get to where you're going, everything is possible. Let me just put it that way. And so what we saw when we learned about the way that the mission would be operated, we as scientists and those in the science operations team, we saw opportunity. Because every time that we place a waypoint, that means that as we go through the think cycle, which is also within the frame of about 4 to 5 minutes worth of think time between these waypoints, sometimes faster, we could actually galvanize our science team, organize our science team such that they could be embedded in the decision of where to place that next waypoint. This is really game-changing, really a paradigm shift from the way that mission operations is typically run with NASA missions. And so we embedded science presence in the mission operations team, in the drive team. So they were right up front, with the drivers. And there is also an organization of the science team who are co-located in the mission building, and are able to actually, in an organized, structured manner, input to the decisions that are made as we move across the lunar surface. So this is a recent kind of application of the work that I've been doing over the last little while towards the development of real-time science decisioning systems. But I do want to take a kind of temporal step back for a moment and talk about the work and where it came from and how it's evolved over the years. And so one of the projects that took place that has really been impactful towards our designs and the way that we have been thinking about how to bring the scientists together, how to help them collaborate, be responsive in a tactical manner to the incredible intensity and tempo of the Viper mission operations, is this project here called Basalt. So Basalt was an analog research project that was laser focused on trying to understand this question here, and that was whether or not across Earth-Mars communication latencies, we could have meaningful, science-focused, bidirectional exchange, and whether that could be enabled during EVAs between scientists and subject area experts on Earth and a crew on Mars. So fundamentally, if we go back to that cartoon showing that there are communication latencies that grow, of course, and become quite lengthy as we move from the Earth to Mars, one of the kind of prevalent thinking or thoughts in the moment as we entered into the Basalt program was that a great deal of autonomy would have to be given to the astronauts exploring, conducting science on the surface of Mars once we reached kind of longer latencies, anything greater than 5 minutes one way. So we really wanted to put that to the test. And so we went into different analog environments. We worked in the Kilauea region of Hawaii, as well as Craters of the Moon National Monument and Preserve in Idaho. And what we did is we worked with the science team to come up with geobiological science goals that we had to actually attain in order for so many of our graduate students to graduate, for people to get, our senior science members to reach their different career milestones. So the science was very much there, present, and required for us to meet. And then from there, we created experimental architectures to examine the conduct of scientific exploration under the conditions of Mars exploration. So this is a drawing that illustrates the architecture that we put together. All of it was built with, really the consideration of the DRA 5.0, again, that was published in 2009. And then from there, we took those considerations and then evolved it into what you see here, which is where we have a co-located science team, a mission science center, mission support center that was meant to be located on Earth. And then we actually had a group of trained individuals who were going out into the field acting as astronauts, but who were acting in the stead of science as well as operations astronauts. And so we had two people that were meant to represent those two domains, go out and conduct EVAs on behalf of the graduate students and the other scientists that stayed on Earth. So we didn't actually allow our scientists who were concerned with the publications, with the data quality, et cetera, go out into the field. But we spent a great deal of time. In fact, 92% of our project time and space was really spent in preparation. Only about 8% was spent going out doing the glamour work in the field. But once we got there, this is the setup that we put into place and that we activated to. And so we were separated between the two groups by about 15 to 20 kilometers. So really there was a solid separation. And then we also instituted communication latencies between the Earthbound team and those that were out in the field to, again, experiment with the latencies and put into that experimentation the process, the procedures, the EVA architectures that we designed with the science and exploration and the optimization of science return really at the forefront, and as well the humans at the forefront of that design. And so what we came up with are timelines and EVA architectures that examine the prospect of allowing intellectual breathing space to exist, both within the science team on Earth, the astronaut team on Mars, and then between those two planetary systems and the communication that we put into place, despite the fact that there were latencies that were instituted between our communications. So I'm going to show you a series of cartoons that kind of illustrates how these EVAs were designed. They were called circuit sampling EVAs. And so we had the astronauts come in and approach one of three typically kind of areas or field sites that we had designated in advance of actually reaching, Hawaii or reaching Idaho through, different sorts of pre-planning and traverse planning sessions. And as they approach these sites, what they would do is a contextual survey. And what was going on in this case is that the astronauts here were transmitting video as well as voice and other telemetry, like their positioning and so forth, back to the crew that was stationed on Earth, and the science team that was stationed on Earth, so the science team could see what they were seeing, albeit over these latencies. But as the data started to come in, the astronauts would then start to put down candidate sample markers that would indicate very clearly where they thought would be the best spot to sample for the geobiological objectives. And they, of course, went into this circuit of contextual survey as well as candidate sample search with the knowledge of what the science goals were. And that came in the the preparation and so forth that I'll talk about in a moment. As the data started to come in to the scientists sitting on Earth, each of them knew what their job was. Each of them knew what their analytical purpose was and how long they had to actually do the work. And what they did is they started to develop pre-sampling priorities. So we kind of started broad and started to work our way down until we whittled down to one single sample that would be collected for the geologists, the biologists, and other purposes as well. And so a leaderboard was used to rapidly monitor and manage the decision-making that was happening in the different disciplines and together between the disciplines in the team. So they had to negotiate what they thought were the best samples as the data started coming in. And they had to do so within a timeline that was tactically appropriate for being able to put that knowledge back into the system to affect the EVA as it was actually underway. So the astronauts went through and they actually would go and, as I mentioned, through three different areas. And as they did, the information was making its way back to Earth, albeit again, across these latencies. And as that happened, as the information came in, this team here on Earth was also transmitting their priorities and their thoughts around how the sampling should happen. As that occurred, the astronaut team then was able to kind of get a sense really of what the priorities were that were building in the room back on Earth. There really was that connection that was built. And what happened next is that the astronauts would then move to instrument sampling. So they would actually start to interrogate some of the sample candidate areas with instrumentation, typically looking for instrumentation around the mineralogy or elemental analysis. And that information would then start coming back to the Earth, and the scientists would again go through the process of ranking their best options. So this process continued until eventually the information was given to the science team on Mars, the astronauts on Mars, in exactly which marker the science team on Earth felt was the best candidate. So we did all this work to really, again, figure out if we could affect an EVA safely as it was progressing and provide input from subject matter experts into the process of science and exploration happening on Mars. All of this was going on, of course, in a very intensive manner in real time in both spaces, and then transmitted across latency. But really, there was this kind of fake sense that there was a latency there. It was more of a time pressure than a latency that we had to live through. And so fundamentally, just to distill really what came out of all of this work is that in creating these real-time collaborative systems, it comes down to really understanding and enabling the people, managing and understanding time, and managing, understanding, and democratizing data. So these are three themes that have been carried through, evolved, and tweaked depending on the application all the way up to Viper. So when we look at the people, this sounds very simple, but I think earlier, I think our moderator Eric might have been the one that said that a lot of times, science is driven by instrumentation. And for us, we really had to build into the perspective of our designs that it isn't just about a robot or an instrument. It's about people. It's about collaboration. That really has to be front and center when you start to design a work system where people are interacting. You have to know how they're going to work, who's on your team, how to optimize the science, not just through the instrumentation, but through the people themselves. We also, really have found time and again, this may seem like common sense, but it isn't necessarily commonplace in terms of its application, that people thrive when there is structure. And they thrive even more, in my opinion, when they are working to a structure that they help to create. And so the process of actually bringing together all of these different disciplines and creating an environment which was culturally unique, that took time, that took effort. And I will always press that operations can't happen later on in mission development. It really should be from the beginning, because operations really comes down to creating a cohesive collaborative culture. Finally, we really have found that physically integrating science and science representation into real-time mission operations is deeply impactful. What I mean by this is, as I mentioned, our astronaut team that went out into the field was always inclusive of a person there that was meant to represent science, and they had to understand the science very deeply and completely. We've also found this with subsequent analog missions, as well as with Viper, where we have a real-time scientist and a science lead embedded with the drive team of Viper, and they're there representing the hive mind of the science team, the Viper science team, and all the decisioning and all of the good stuff that's coming up from that hive mind and being distilled and then kind of reconstituted for the drive team by the science lead and the real-time scientists. So that physical representation, again, coming back to the people, is so incredibly important. Along the lines of people, one thing that or many things really, that we spent a lot of time doing with each project, and in particular with Basalt, was really trying to get the scientists to articulate what their goals were, very carefully moving from their hypotheses into their direct tasks and then the kind of instrument needs, because that was a very important traceability document that allowed us to deconflict many of the areas where some friction had built up in the system, particularly between the competing biological and geological goals. We also spent a lot of time creating, it seems very commonplace, a field glossary, but this was our field glossary. Our cultural, kind of existence and our parlance was really measured by this field glossary, because as talked about on the panel, there's a matter of jargon, and that can be very jarring, in my opinion. And so we spent time trying to share the jargon across all the domains, not only science, but engineering and operations, and then to educate the team internally, which were 50 plus people, across the domains as to what each terminology meant, which ones did we think would be the most important while we were conducting these EVAs, having scientific discourse, et cetera. And in fact, some words meant different things to different groups, and that was very important to deconflict right from the get-go. So all of these types of tools that were developed by the people for these people have, they've basically lived on through time in terms of their importance from project to projects and right up into mission operations to this day. We'll also tell you that the clarity of communications was part of our experimentation with Basalt. We knew that we had voice, we had visual communication tools. We also had chat, and we wanted to understand the importance and the difficulties and how we might increase the efficiency of chat. Chat is part of our lives. Everybody chats all the time. But when you're actually in mission operations in these intense operational environments, chat can be an entirely difficult beast to wrangle in if it's not wrangled from the beginning, from the get-go. So we looked extensively, again, at the manner in which our team would be working, at where the kind of expeditious elements were that chat could help with, and where voice could be much more expeditious and so forth and efficient. And then we tried to clean that up and evolve it through each and every outing that we had. We had 3 different field outings during the Basalt mission. And there, I should have mentioned earlier, pardon me, but there is an entire special issue which is open and available through astrobiology. And so you can read about the details of these experiments and the output in that special issue. If you just Google basalt and astrobiology, it will pop up and you can download everything. I also want to talk about time. So we built with the Playbook team at NASA Ames. They're a group of individuals who fundamentally create these incredibly complicated and yet very you can really work with these mission timelines that the Playbook team creates. They're very approachable. I guess that's the best way I can put it. And so we worked with them to create process, procedure, and timelines in order to manage across and within each of the work domains. So when I say across, I mean between planetary destinations, the Earth and Mars, as well as within our teams themselves, to keep them on time with their decisions, and so that everybody knew when they had to produce certain analytics, certain decisions, and distill their group's discussions down to a decision. And so all of that was very important. And we examined some of the decision-making architecture that was involved with the EVAs and the management of those EVAs, as I kind of described at a high level in the earlier cartoons. We also looked at portable instrument suites and tried to understand when they would be most valuable. Again, there were so many competing conversations about what instrumentation would be valuable to bring out into the field, but it always came down to what could we work with and when during an EVA that would provide substantial, a substantial uptick in our knowledge base around what sample we wanted to have collected, and how might that help us really triage the different sampling opportunities. And so that's what this paper is about. And we designed, again, within the timelines for each of the EVAs were much more refined timelines that all the different teams and the instrument teams were managing. Finally, around the realm of data, there's so much to talk about there, and so much that has sort of evolved coming out of Basalt, moving into other projects. One of the elements that we really wanted to examine is what type of data system, what type of ground data system had to exist to support real-time collaborative science, to democratize the access of science and exploration throughout our mission team, and how might we actually work with that access in order to enable science discovery and science discussion overall. So what we've come down to is that really a data system that supports real-time science decisioning has to enable a shared operational and scientific awareness across the team. We've found that if we sort of cleave off portions of what data are available to a science team and only push them to certain stakeholders, that it really creates very difficult, very inefficient conversation between groups. Because if you don't see what your other colleague is seeing, then right away you have friction points in the system. And so what we advocate for, what we have advocated for, again, in the Viper mission as an example, is just a democratization of access to create this shared awareness. And that leads to the second point of enabling collaborative science decisioning and discussion. And finally, we really believe in a system that allows for rapid replanning, not just by planners, not just by timeliners, but by the scientists themselves. And of course, through process and protocol, you can create different levels of and triage mechanisms in order to manage the replanning. But any data system that we have seen really beneficial for science, particularly in the realm of real science decisioning, has enabled rapid replanning. I'm just going to touch briefly on a project that came out of Basalt. We moved into an oceanographic setting where we wanted to then take these principles of looking at how to enable data systems that supported real-time science decisioning and put them to the test in a different environment, in oceanographic exploration. The oceanographic community has used telepresence for many years now to enable scientists onshore to participate with those that have the joy of being able to be at sea. And typically there's this much smaller group of individuals that get to go to sea and conduct all of the scientific research for those that stay on land. Again, very much, a great analog to space exploration. So we managed to get a project funded through NASA that involved the natural sciences, very much focused on astrobiology questions, as well as social science research and exploring the mechanisms for actually creating this synergy, this collaboration and culture within the group to really enable this real-time decisioning. And then we delved further into the technology and the data systems and what might actually be beneficial not only to the oceanographic community, but that would be extensible to missions such as Viper. So we went to sea on the Nautilus and conducted a variety of different experiments. We both observed the oceanographic community as they, quote unquote, existed in their telepresence architecture. And then the second time we went to sea, we actually instituted some experimentation where we looked at latencies that were created and opportunities that were created operationally that were very much akin to operating in space. And as I mentioned around the data, we took the time with this project to focus on data access and visualization. Our goal was really to provide a shared awareness of the exploration environment so we could enable collaborative real-time science decisioning between those that got to go to sea and those that we actually enabled to participate with this at-sea exploration 24/7 who had to stay on land. And so again, we found, just to cut to the chase, that really providing timely and ubiquitous data access to like all the data across all of subsea work domains and locations was truly important to the team. So some of the tools that we worked with was actually enabling scientists to author map layers for interactive visualization, while both in the planning stage of the mission as well as while the mission was going and taking place in real time. And so you see someone actually moving through the screen right here, and then clicking and then annotating in these map layers. I'm just going to scroll through. You see them turning on and off different map layers here. Let me see if I can move us forward. And what this, as the mission progressed and we were gathering input, what this really did for the scientists is it allowed them, again, across both the ocean, those that were at sea and those that were on land, quick access to different data layers so they could, all see the same thing at the same time, talk about what they were seeing as the mission was progressing. That was a highly powerful component of what was provided through this system. We also, talking about replanning and collaborative replanning, enabled the team to work together both onshore and at sea, and then across those work domains to actually plan together in a meaningful manner. And those that were onshore were able to use this tool to actually respond to what was coming in and to make better decisions about where they might direct the ship next. We also enabled the team to take frame grabs of data that was coming in from the cameras on the ROVs that were interrogating our field sites and annotate the image and share this across all of the different workstations that were on land, as well as then send key, directional, kind of decisional images back to sea. So all of this work was ongoing and, allowed us to kind of refine some of the data systems that we had over the years really identified and then finally had the chance to really work on in deeper detail with the oceanographic community as our kind of main platform. I also want to tell you that as part of the data system, we really wanted to highlight active team participation, being able to record events, share events that a scientist felt was important and then go back to later. I cannot press enough just how intense the mission was, in terms of operating 24/7, in terms of the rate of of intensive kind of exploration. Even though we would sit still, there was never a moment where you could space out, to come back to some of to the earlier question. You really had to be engaged. And so what this tool allowed us to do is to have the scientists be engaged with the mission, but also with each other so that they could share their thoughts across each and every moment. these are some of the bits of feedback that helped us to, take a look at the value of some of these component parts and how to improve them and evolve them as we move forward. The other thing that we did for the science team was to talk with them about their needs to really see all the data together in a synchronized manner so that they could temporally understand what they were seeing across the different instrumentation. So again, the instrumentation is important. However, what's really important is our interpretation of that and how we learn from that so that we can then put what we're learning back into the system. I'm just going to scroll forward here. Hold on one second.
Darlene, I think we only have a couple more minutes.
You got it. I'm coming to the end, except that I'm having some tech difficulties here. Hold on one second. Okay. I just wanted to also add that one of the key components of the data system that we developed was the opportunity to export data for other users and other analytical systems. This has become, again, an aspect of the data system which continues to be important and highlighted through different applications. And again, was built in to the system to allow for across the board users to gain access and then do their work as they need it. As I mentioned, hopefully this video is actually moving at your end, coming full circle back to the moon. The work that we're doing for Viper, again, stems from so much of this analog work that took place on Earth, and so much of what we're learning we know is going to be extensible to future lunar missions as well as to Mars. I do want to let you know that as an example, one quick example, this data visualization and the shared access to the visual data is so important to us. We spend a lot of time thinking about, as we delve into the traverse areas, how do we create a shared vision of what we're actually looking at? This is obviously an orbital view of where the rover is positioned. This is from one of our simulations. And you see that, you see where it is, you see what's around it, but really, when we start to look at some of the imaging that comes back from the rover itself, these are all simulated data, simulated images. You really still get a sense that you're looking through a portal, a very small lens. And so in terms of creating a shared collaborative environment, there are limitations. And so taking and learning from what we have done in the past, we realized that we had to create a way to enable folks to rapidly look at panoramas, so real-time generation of panoramic images, and also to provide context as the scientists are scrolling through, so that, again, they all are situated in the same way. They all understand where we've been, what we're going to do, and what we're looking at. There is one more slide that I will show you, if I can get the system to stop and hopefully scroll forward. Let's see here. I'll just pause there if we have questions about that. But I do just want to close with this remark that as we've built the real-time collaborative systems from the foundation of so much of this analog work and other analog work, and progressed into the application towards sending assets back to the lunar South Pole or onwards to the lunar South Pole, and then eventually with humans, we've always had to look to the past to see what we could learn, and that has been very important for us. The Apollo science team worked in a back room, and they worked in a particular manner, and we've had to really start from that, deconstruct it using different social science tools, and then reconstruct it in a manner that was meaningful for Viper, and then of course evolve different learnings from different communities and experiments, as I just talked about, over time. And so as I put this up, I want to stress that a lot of our work going into the application of what we've learned around real-time, establishing these real-time collaborative systems, has involved comparatively looking across different NASA missions, different international missions, different experimental opportunities such as analog work, and trying to figure out what is relevant, what isn't relevant, and where are the spaces where we need to innovate because it's in the new. And so this has been really a significant part of our work, and one that I wanted to end with because I think that's the beginning of what we do next. Thank you very much, everyone.